Hi guys, Daniel here, and today we're going to prove Euler's identity, which some people argue is the most beautiful identity in mathematics, because it combines a bunch of random mathematical constants, e, I, pi, 1, and 0, and combines them into an equation. So let's first, in order to prove this identity, first I will consider a seemingly completely unrelated function, which is this function. F of theta is equal to cosine theta plus I sine theta. So let's first observe some properties of this function. Well, if we try to take the derivative of the function, f prime of theta, then it turns into negative sine theta plus I cosine theta. This seems quite a bit like the original function, actually. And if we think about it, this is actually just equal to I times f of theta. So that's pretty cool. We have the derivative of this function is actually I times the original function. So how might this help? Well, we can try taking this equation and try to solve for f of theta again, because this is basically just a differential equation, and we can try to solve this differential equation. So if we first move all the f of thetas on one side, then we get f of theta over, or f prime of theta over f of theta is equal to I. So now this is in the form of something that we can actually integrate. So let's integrate both sides with respect to theta. Integral of f prime theta over f theta d theta equals integral of I d theta. So the right hand side is clearly just equal to I times theta. What about the left hand side? Well, by the chain rule, we know that this thing is equal to the natural log of f of theta, and that's it. So of course we have to add the plus c. And now we need to just first find the value of c, and then we can solve for f of theta. So what do we know about this function? Well, we do know that f of 0 is equal to cosine 0 plus I sine 0, which is equal to 1. So if we plug this in here, then we should expect that to be true. So if we plug it in, we get f of 0 is equal to 1, log of 1 equals to 0, and I times 0 is equal to 0, so that means c must equal to 0. So we get that log of f of theta equals I theta. And now, almost done here, we just take the exponential of both sides. We get this f of theta equals e to the I theta, which, recall from our original definition, is equal to cosine theta plus I sine theta. Alright, so now we are almost done here because we want e to the I pi, not e to the I theta. So let's consider what happens when we evaluate it at pi. F of pi equals e to the I pi, which is also equal to cosine pi plus I sine pi. Well, sine pi is just 0 and cosine pi is negative 1. So this entire thing is just negative 1, which implies that e to the I theta, or e to the I pi plus 1 is equal to 0, which is exactly Euler's identity. So if you were astute, you may have noticed that there is one part of this proof which is slightly questionable, which is this part from here to here. Because the thing is, f of theta is a complex function. It outputs complex values. And somehow we're saying that this integral is equal to the natural log of f of theta. And we're not even sure what the definition of the natural log of a complex number even is. So we're not quite sure if this integral is actually true. And in order to make this 100% rigorous, we would need to have a definite definition of the natural log over complex numbers. But since that's a little too nuanced for this video, I'll just leave it out for now. So I guess you could call this a morally correct solution, a proof of e to the I theta plus 1 equals 0. So of course, if this is unsatisfactory, if you really don't like how I kind of fudge the definition of natural log, we could also prove it another way, which is using the Taylor series of e to the x. So recall that the Taylor series of e to the x around x equals 0 is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus etc. And well, we want to show that this expression is true. E to the I theta equals cosine theta plus I sine theta. So let's plug in I theta in for x, and we get that e to the I theta is equal to 1 plus I theta minus, because the I times I is equal to negative 1, theta squared over 2 factorial minus I times theta cubed over 3 factorial plus theta to the 4th over 4 factorial plus I theta to the 5th over 5 factorial, etc., minus da, da, da. And now we want to prove this is equal to cosine theta plus I sine theta. So, of course, we will consider the Taylor series of cosine theta and sine theta as well. The Taylor series of cosine theta is equal to 1 minus theta squared over 2 factorial plus theta to the power 4 over 4 factorial minus theta to the 6 over 6 factorial, and so on. And the Taylor series of sine theta is equal to theta minus theta cubed over 3 factorial plus theta to the 5th over 5 factorial minus etc. So once we multiply sine theta by I, we get that all of these now have i's in them. And once we add these two together, we find that this is equal to 1 plus I theta minus I theta squared over 2 factorial minus I theta cubed over 3 factorial, etc. And this is actually exactly equal to the expression for e to the I theta. So again, we get that e to the I theta is equal to cosine theta plus I sine theta. We plug in theta equals pi, and we get that e to the I pi plus 1 equals 0, which is another proof of Euler's identity. Hi guys, it's Daniel here. Recently we did a test, a team selection test for the Washington State HMT and PUMAC teams,